Hello everybody. In this video, we're going to touch on how to actually find indefinite integrals. Okay? So in the last video, I mentioned to you the inverse power rule. The inverse power rule as a powerful tool for integration. Okay, and it's the most basic rule you will learn. When taking an integral of this form, x to the n dx, where dx is your variable of integration. The integral of x to the n dx will be x to the n plus 1 over n plus 1 plus c. Okay? Where n is not equal to -1. Now, as I said before, we'll cover the case where n does equal -1 in a later video. Okay? And you could kind of see how this formula sort of makes sense. If we look at the normal power rule, we see that the derivative of x to the n with respect to x is n times x to the n minus 1th power. So you're decreasing the power when taking the derivative. So the inverse of that, or the opposite of this integration, will increase the power. You're multiplying by the original power. Now you're dividing by your new power. So you can sort of see this reverse relationship over here between the inverse power rule and the normal power rule. Now we're going to use this and actually apply this to some integrals. So let's try to find the integral of x to the 5th dx. So this gets us, if we apply the inverse power rule, you get x to the 6 over 6 plus c, where c's are constant of integration. Remember, you have to put that c in there. Otherwise, you're not actually finding the antiderivative. Now, if you want to, you don't always have to take one-term integrals. In fact, almost never take one-term integrals. Usually take multiple-termed integrals, and that's where we learn about some of the most basic properties of integration. Okay? So many of these actually match with differentiation. Okay? So when we look at differentiation and integration, or indefinite integration. Now, for differentiation, the derivative of some constant term k, a real number, times a function equals k times the derivative of the function. So you're basically pulling out your constant. You're pulling out that term from the derivative. The same can be said about integration. Okay? The indefinite integral of k, where k is a real number, times f of x dx is equal to k times the integral of f of x dx. Okay, so you can also pull out the k when you're taking an integral. When you're taking the derivative of a sum or difference of terms, plus or minus, this means either sum or difference, it's the same as the derivative of the first function plus or minus the derivative of the second function. The same thing can be said about integration. The integral of f of x plus g of x dx equals the integral of f of x dx plus the integral of g of x dx. G of x dx. I have to fit it in there. Okay? And the derivative of a constant times x is just a constant, right? So the integral of a constant term is equals to constant times x. Remember, you're getting the same thing. Like when you're integrating this, you get this. When you differentiate this, you get this. Okay? And you can use this connection to get a whole bunch of integration rules for the trig functions. Okay, if you remember the trig functions, the integral of sine of x dx, well, what function can you take the derivative of to get sine of x? Well, you can get, it's not cosine of x. Since the derivative of sine of x is cosine of x. It's negative cosine of x plus c. Okay? Negative cosine of x plus c. And if you take the derivative of this, you get sine of x. And you could do this, do the same thing for cosine of x. The function which has a derivative of cosine of x is sine of x plus c. You can say the same thing for secant squared of x. Dx equals to tangent of x plus c. The integral of secant of x tangent of x equals secant of x plus c. The integral of cosecant squared of x dx, should put a little dx there, equals negative cotangent of x plus c. And the integral of cosecant of x times cotangent of x equals negative cosecant of x plus c. Now you might be wondering, where's the integral of tangent of x and normal secant of x, normal cosecant of x, and normal cotangent of x? As a matter of fact, we have much more complex forms rather than the simple forms. I mean, we don't have an integral for normal tangent of x. We don't even have an integral for normal secant of x, yet we have an integral for secant squared of x. And this happens because when we take the derivative, if you look at the antiderivatives of all of them, they're all 6 of the basic trig functions, just with some of the signs are messed up, okay? And that's why we can only integrate more complex forms, because the derivatives of the original 6 functions result in the integrand, which is this little function that you're integrating, okay? So enough talk. Let's actually start integrating, taking some definite integrals. Okay. Let's take the integral of 3x to the 4th minus 5x squared plus x dx. Now you just separate it into the corresponding integrals. You're separating the integrals. Okay, you can separate the expression and take the integral of each individual term. That gets you 3x to the 5 over 5, 3x to the 5th over 5, minus 5x cubed over 3, plus x squared over 2. And can't forget plus c. So this is our integral. So integration might not seem so bad now. Let's look at this one. This one's a little more fun. X plus 1 over the square root of x plus c. Oh, not plus c, dx. X plus 1 over square root of x dx. Now, this does not equal this. Just like it's not allowed in differentiation, this is not allowed in integration. Okay? So this is completely wrong. What you would do is you would separate these. Separate the fraction, and then take the integral of each term. X divided by the square root of x is just the square root of x. Or you could rewrite this as x to the 1/2 power. And now you can see where you can start applying your power rule, or should I say the inverse power rule. 1 over square root of x equals x to the -1/2 dx. And this inverse power rule applies for all real numbers. Okay? So you have, if you integrate this, you get 2/3, that's 1 over 3/2, because 1/2 plus 1 is 3/2, times x to the 3/2 power plus 1/2 x to the 1/2 times 2, because 1 over 1/2 is 2. Remember, we're just applying the power rule here. Okay? And this is our answer. You can turn it into a radical form if you want. You can actually factor out 1/2. Okay, you can actually factor, this happens way too much. Okay, you can actually factor out x to the 1/2 and you get 2/3 square root of x. You want to rewrite in the form I was given to you. So no fractional exponents if it didn't give you fractional exponents. So square root of x times x plus, well, 2/3 times 3 equals 2. So 2/3 square root of x times x plus 3 plus c. And this is our integral. Okay, so you cannot take the integral of each term in their quotient, but you have to find a way to separate them and use our power rule. So let's do one more. Let's do a trig one. Okay, let's do a trig one. We want to find the integral of cosine of theta over 1 minus cosine squared theta d theta. Okay? Now, you can't really separate this fraction since the actual difference is in the denominator. You can't integrate each term in your fraction. You can't integrate the numerator separately from the denominator. So it looks like you give up. No, you do not. Okay? Because the bottom one should be kind of familiar to you. It's a trig identity. Okay, you could use the fact that sine squared theta plus cosine squared theta equals 1. So sine squared theta equals 1 minus cosine squared theta. So you can just replace this with sine squared theta, d theta. And now this starts to make it a bit better, a bit cleaner, because you can separate the product as cosine of theta over sine of theta times 1 over sine of theta. 1 over sine of theta d theta. d theta. And cosine of theta over sine of theta, this equals cotangent of theta times cosecant of theta. And if you remember, this is one of our integration rules. The integral cosecant of x times cotangent of x, this equals negative cosecant of x. Our answer is negative cosecant of theta plus c. So these trig integrals, some of them can be solved with trig identities just like this one. Now you might be wondering, is this all integration is? The answer is no. In the next couple of videos, we'll learn about lots of different types of integrals and its applications. Thanks for watching. If you have comments, please comment below.